In the last couple of videos, we've talked about entropy. What does it mean? How do you calculate it? In this video, we're going to talk about the second law of thermodynamics, which is the whole reason we've been talking about entropy. So the second law of thermodynamics states that the entropy of the universe increases in any spontaneous process. The universe part is really, really important because the calculations that we were doing before only talked about the entropy of the system. But remember that the universe is not only the system, it is also the surroundings. I'm also going to address this term here, spontaneous. In chemistry terms, spontaneous doesn't mean the same thing as it does colloquially. Colloquially, spontaneous means something that's happening quickly and right away, whereas in phys chem terms, spontaneous just means thermodynamically allowed or possible. So try not to let that term confuse you. It is not the colloquial definition of spontaneous. So we could rephrase the second law of thermodynamics to say that the entropy of the universe, which is the combination of the system and the surroundings, must increase in any process that is thermodynamically allowed. And that would be a more thorough and accurate law, although it would take a whole lot longer to say. So let's apply this to a real-life situation, one with which we're quite familiar, and that is taking water and putting it in our freezer. We know that water does, in fact, freeze. So we know that this process must be thermodynamically allowed, and yet our discussions of entropy would suggest that the reaction going from liquid water to solid water should be one that would have a negative entropy change. We discussed the idea that the water molecules being in a crystalline arrangement and having restricted numbers of positions they could occupy and orientations they could have would mean that the entropy of the solid water would be smaller than the entropy of the liquid water. And so when you took entropy of the products and subtracted entropy of the reactants, you're going to get a negative value for the entropy change. But the second law of thermodynamics says that's not possible. And the reason that the reaction can go, even though the entropy change for the water is negative, is because we need to factor in the surroundings as well. For the water to be allowed to freeze, we must be increasing the entropy of the surroundings, in this case of the freezer and the air in the freezer, by at least as much, if not more, than the amount we're decreasing the entropy of the system. So we saw last time that the heat change for this process was equal to negative 6,007 joules per mole. And we were therefore able to calculate the entropy change for the system by saying that that would be equal to the enthalpy change for the system divided by temperature, which is negative 6,007 joules per mole, divided by the water itself in the act of freezing is at 0 degrees Celsius, so 273.15 Kelvin, which gave us negative 22.19 joules per mole Kelvin. So where did that heat go? The heat has to go somewhere. It can't just disappear into nothingness. And where it went, of course, was out into the freezer, out into the surroundings. And so we can also calculate an entropy change for the freezer, for the surroundings. And it will be equal to the enthalpy change. It's actually the heat change, but because we are functioning at constant pressure, the freezer is not pressurized. It's just operating at atmospheric pressure. So we've got an enthalpy change there divided by the temperature, and this is of the freezer. So part one was the water/ice, which was at 0 degrees C. Part 2 is the freezer, which is at minus 20 degrees C. And so the water released 6,007 joules per mole of heat. That's why there's a negative sign on the enthalpy change for the water. The freezer is absorbing that heat. So it has a positive sign on its enthalpy change. It absorbed heat. And we have to divide that by the temperature of the freezer, which is minus 20 degrees Celsius, which again must be converted into Kelvin. So we add 273.15 to that, and that gets us 253.15 Kelvin. And that gives us an entropy change of plus 23.73 joules per mole Kelvin for the surroundings. If you want to know whether or not the process is allowed, you must then calculate your entropy change for the whole universe, which is equal to the entropy change for the system plus the entropy change for the surroundings, which is equal to negative 22.19 joules per mole Kelvin plus positive 23.73 joules per mole Kelvin, which is equal to plus 1.74 joules per mole Kelvin. And so, in fact, it is thermodynamically allowed for water to freeze and give you ice cubes if your freezer is at negative 20 degrees Celsius. And in fact, if you were to do the math, it is thermodynamically allowed for water to freeze at any temperature below 0 degrees Celsius, because in each of those cases, the warming up of the surroundings results in a greater entropy increase for the surroundings